Hey guys, so this is the gas pressure demos worksheet. We're going to start off with some definitions, and then I'm going to show you a barometer. It's a little bit different from the barometer in the book, so I'm going to show you how that works. We're going to talk about it a little bit. Well, I'm going to talk about it a little bit. Hopefully you'll be actively engaged. Okay, and then I'm going to talk about the atmosphere bar, and if you want to experience the atmosphere bar, you're going to have to come and see me or Miss Varka when we do get back in the building. So even if it's next year, come see me, and it's a pretty cool thing, and hopefully I can get you excited about it. And then the second video is going to give you the balloon demos. This is a video we made last year because we kind of ran out of time. We had a shortened day, and we needed to make that video for last year, so that one's already made and that one's already ready. Okay, but we're going to start off with some definitions, and pause as much as you need to in order to get these, but I'm also going to talk through them, give some examples, be a little more descriptive. Okay, so first off, I have definitions for an open system and a closed system. Okay, so open system, we're talking about gases. So a container that allows movement of gas into and out of it is going to be an open system. So if you just have a cup that's open, the air can go in, air can go out, it is an open system. Okay. Other examples, even a bottle, as long as the lid is off, it's an open system. As soon as you put a lid on that bottle, it becomes a closed system. So it does not allow the movement of gas into or out of the container. Okay. A balloon, open system until you tie a knot in it, and then the air inside can't move in and out, the air outside can't move in. So we're looking at a closed system. Okay, so you can have an open container and then close it, but just wanted to give you guys those two definitions. Pause if you need to, but I'm going to go ahead and flip it over to the next side. Okay, so rigid and flexible container. Again, we have probably used those words before, so they're not new to us, but we're just going to talk about them in a little bit more technical language here. A rigid container does not change size with changes in pressure or manual adjustment. Okay, so if I have a glass bottle with a lid on top, a hard lid, this is not going to change size. If there's a pressure buildup inside or if there's a pressure change on the outside, this is not going to change size. I cannot change size manually either, so I can't manipulate its size. It's a rigid container. Okay. If it's a plastic bottle, okay, generally we would consider something like this to be a rigid container as well, because if we heat it up or increase the pressure on the inside, this thing's not going to get any bigger, but it's got a little bit of flexibility to it. So these two, there's going to be kind of a spectrum of container types. So you could have mostly rigid, mostly flexible, some kind of combination, okay, highly flexible or highly rigid, okay, but does not change size with pressure or manual adjustment. Okay, so flexible container does change size based on pressure changes, or manual adjustment. So a flexible container, really simple, balloon. If you have a balloon and you heat it up, it's going to expand because the pressure inside is going to change. Okay, so balloon is highly flexible. Another example is a syringe. Okay, so the syringe that we saw in the laboratory in the last unit, that would be a flexible container. Now it's a hard plastic thing, but because you can pull on the plunger or push the plunger in, it can be changed with manual adjustment. Even if I put a cap on the end or a stopper, okay, I can make the volume change by changing my force on that plunger. Okay, so that's a flexible container, even though it might appear rigid at first glance. Okay, those are those definitions. Now we're going to go into kinetic molecular theory. So this is a big part of chapter 13, and we're really referencing it with gases. Okay, so we really want you guys to understand how gases behave. Okay, so definition of kinetic molecular theory. It explains states of matter based on the movement of particles. And it's all states, okay? So we've already talked about solids. The particles are vibrating in place, okay? Liquids, they're rolling around each other in the liquid, and they're still in contact. But now we're going to talk a lot more about gases and how they behave. We've been drawing particle diagrams, but we really want to get into the nitty-gritty of gases. So assumptions to help us understand the behavior of gases. Number one, and I know there's 4, you'll have to write small or get another piece of paper if you want to get the full definitions here, okay? But number one, particles are small, hard spheres, okay? Now we talked about this a little bit. That's not exactly true for all gases. It's true for our noble gases because they exist as little individual atoms. All other gases, it's not going to be perfectly true, but we're going to use it as an assumption to help us understand their behavior. So please, this again, assumption for gases to help us understand their behavior. So they're small hard spheres. They have negligible volume. The particles have negligible volume. The gas takes up space because those particles are flying around, putting pressure on their container and etc. Okay, so the gas takes up space, but the particles themselves are such a small volume compared to the volume that the gas takes up that we're going to say they have negligible volume. Number 3, they don't attract or repel each other. They don't attract, no attractions at all. Again, this is an assumption. Everything has at least dispersion forces, but we're going to keep going with it, okay? No attraction, so when they bounce off each other, it's got a predictable change in trajectory, okay? And they have rapid motion in straight paths until they collide with something, okay? So a lot of this was very similar to what we wrote in our chapter 13.1 notes, okay? But rapid motion, straight paths until they collide with something. They don't just fly around like little squirrely things, okay? They have to hit stuff in order to change directions. Okay, moving on from kinetic molecular theory, we're going to go to types of movement. So we're going to get, again, some technical language for things that we've already been visualizing. So we've got 3 major types of movement. Translational is going from one point to another point. So it's actually moving, it's covering some ground. And that's the main type of motion in gases, okay? We might get a little bit of that in a liquid, but mostly that's going to be what we're looking at in gases, okay? Rotational, spinning on an axis. That's going to be what we're looking at with liquids, where they're kind of rolling around each other. So their major motion is going to be rotational movement. A little bit of translational, but this is the major motion for liquids. And then vibrational, again, movement in place. That's going to be what we see in solids. Now, again, gas particles and liquid particles can vibrate as well, but it's not as noticeable as the other type of movement that they have. Okay, so vibrational is our major movement in solids. All right, next definition, gas pressure. Force per area caused by collisions of particles with the surface. Okay, so collisions with me, collisions with this, collisions on the inside of a balloon, all of those collisions is gas pressure. Okay, that is just such an important word when we're talking about gas pressure. So please, please, please make sure that you connect that to gas pressure so you can think through some of the problems that we get to. Okay, all right, our last definition was temperature. I didn't have room on my little whiteboards for that, so I'll just go ahead and write that out. This one was also in your notes packets, but temperature, hopefully you already know it, but if not, we're going to try and get it into your brain by writing it again. It is the average kinetic energy, so again, moving energy, average kinetic energy of all particles, average kinetic energy of all particles in a substance. Okay, so higher temperature means higher average kinetic energy, which means faster movement, more movement, okay? So kinetic energy is moving. Temperature is the average measurement of that movement. So the faster things are moving, the higher the temperature. Slower things are moving, the cooler the temperature, okay? It is the same. Please connect those in your brain as well. Okay, we're going to get into our first set of demos, okay? So we've got a barometer. You already have a picture drawn on your sheet. We used to have everybody draw their own picture, okay? But people have different abilities of drawing, but just give me a second here so I can draw out a barometer because I forgot that you already had yours drawn. All right. So it looks like this. Straw, stopper, bottle, something like that. Anyway, okay, don't judge my drawing skills. I'm a chemistry teacher. Okay, so over here, this is the barometer. We can kind of see it, hopefully. I'll try and bring it a little closer to the camera. Now moving it is going to affect the water level here. But if you can see, this is just water. I put green food coloring in it. There's water inside the straw. And when I put the stopper in, I pushed down on the gas that's trapped inside here, okay? And that pushed water up into the straw, and the water level in the straw is up here, okay? So our first task is to shade the picture and show that water level, okay? So you can go ahead and use your drawing skills, but shade, in the bottle here is out like that, and then the straw has water all the way up here into towards the top of the straw, okay? So something like that. If you want to be more artistic than me, you go for it. I don't know. I don't want to mess up my markers, okay? But yeah, water here inside the bottle, and then water way up here in the straw, okay? I'm going to lower that water in the bottle here just because I want to be able to draw some other stuff inside the bottle. Okay, so next, circle one of each of the following as it applies to our barometer, okay? So is it open or closed? Remember, that's referring to gas particles being able to leave or enter the system. So right here, I have gas trapped inside. It cannot leave. Water can move up and down in the straw. Air can go into the straw up here, but it cannot get to the gas that's trapped inside the bottle. So it is a closed system, so please circle closed. Rigid or flexible? Again, if you're just focusing on the glass, you're going to say rigid, okay? But even as I moved it over to you, the water level was changing in the straw. And if the water level is changing in the straw, that's because the volume of the gas inside is changing, okay? So if the gas inside expands, it's going to push that water down, which is going to force it up out of the straw, okay? If the gas inside shrinks, contracts, condenses a little bit, then the water is going to be able to come back down into the container. So this is a flexible container, even though just a tiny little circle of area is able to move up and down, it is a flexible container. So please circle flexible. All right, 3, draw arrows to show where there is air pressure in the system. So what is pressure? I hope you're thinking of a C word in your mind, because it is collisions of gas particles. So collisions is pressure. Where do I have gas colliding with something in this system? Okay, where? Well, I have gas trapped in there, and it's flying all over the place, colliding off of stuff. So we're going to draw some arrows inside. It's colliding off of the glass. The gas is colliding off of the surface of the water in here. Okay, so colliding with the water, colliding with the straw, colliding with the stopper and the glass in the neck of the bottle, okay? Lots of collisions happening inside the bottle. Now, where else do we have gas collisions? Well, we have gas collisions all outside the bottle too, okay? If you want to draw a couple of those, you can. But the most important place that we need to think about on the outside of the bottle is right here. There is gas flying around in the room, and it's flying into the straw and colliding off of the surface of the liquid, okay? It's colliding all over the straw too, but there is a pressure on top of that liquid. Otherwise, if there wasn't any, that liquid would just shoot out, okay? So we do have some pressure keeping that liquid in the straw and not letting it come all the way out of the straw. All right. Number 4. How does air pressure at sea level compare to Laramie, and explain? Okay, now remember, if you go down in elevation, it's like going deeper in a swimming pool. It's a swimming pool of air instead of a swimming pool of water, but the deeper you are in our atmosphere, the more pressure there is. Got more higher particle density, that's more collisions. Okay, so sea level has higher air pressure because you're deeper in the atmosphere, there's more air on top of you, it is denser, more collisions. Get some kind of explanation like that written, okay? Higher pressure at low altitudes because there's more collisions from a denser atmosphere. Okay. Number 5, again, pause whenever you need to. If we transported this bottle to sea level, what would happen to the level of liquid in the straw? Okay, well, we just said that at sea level there's more pressure. I'm taking this bottle, which is closed, to sea level. So the inside of my bottle is not changing. It's got the pressure that it has, okay? But when I go to sea level, this pressure is going to change. I'm going to erase this arrow, and I'm going to make a bigger arrow. Big, fat, jumbo arrow. Okay? I'm increasing my pressure here. So what's going to happen to the level of the liquid in the straw? Hopefully, you're saying it will go down, okay? The higher pressure at sea level will push down inside the straw and lower the liquid level, okay? And the reason it does that, pushes that liquid down in the straw, which raises the liquid up just a tiny bit inside until the pressure here is equal to the pressure on the outside. When I squash those molecules, they're going to collide a little bit more, and they're going to create an inner pressure that equals the outer pressure, okay? So it's going to push that level down in the straw until they equalize the pressure inside and outside the bottle. All right, so again, it's asking what's going to happen to the level of liquid in the straw. So it's going to go down because higher pressure outside is going to push it down. All right, 6, if the bottle were cooled, so if I put this, it's not really that cold outside, but maybe if I put it outside, or if I put it in a tub of ice, for example, I'm going to cool the system. The outside pressure stays the same, so I'm going to erase my jumbo arrow here as best as I can. Okay, so my outside pressure is going to just stay my normal room pressure, okay? But I'm going to cool the bottle down. Now, cooling makes things move slower. Okay, so if things are moving slower, what's going to happen to my collisions, the number of collisions that I have? If you're moving slower, you're going to collide less often. Okay, so I'm going to take away some of these collision arrows on the inside. They're moving slower now because they're cold, so they're going slow. And because they're moving slower, there's fewer collisions inside. But there's the same number of collisions outside. So again, this is going to go down. It's going to be pushed down in order to create a smaller space here and equalize the collisions inside and outside. So if I have less pressure inside to maintain that water level, it's going to get pushed down. Okay, so get some kind of written explanation there. The liquid level in the straw will get lower because the outside pressure will now be higher than the inside pressure with those slower molecules inside. So it's going to push the water down to even out the pressure inside and outside. Again, kind of hard to wrap our brain around, but you just have to think about it in little steps. All right, that is it for our barometer demo. I don't think I skipped anything. Now I'm just going to talk to you a little bit about an atmosphere bar, okay? So 7, what is a common unit for pressure in the United States? So if you think about getting your tires checked, what unit do they use? So hopefully you've at least heard of this unit before. PSI, that's the tire pressure unit. This is our American unit for pressure, okay? And that is pounds per square inch. Pounds per square inch. So that's what question number 7 is asking. Okay, 8. What is the weight of the atmosphere bar? Now, I don't have it with me. It's at school because it's kind of a crazy thing. It's about, I don't know, a little more than a meter long. It's an iron bar. It weighs 14.7 pounds. Weighs 14.7 pounds. That's the first part of question number 8. Okay, and then what is the area of a cross section of that bar? So it's a square bar. It's not round, it's square. And the area is a square inch. Okay, so it's about a meter long, But if you were to look at the end of it, it's a square inch. So I don't know, like about like that, okay? Square inch. That's probably too big. But anyway, that's about how big our bar is, okay? Now, why is it this weight? I think that's the next question. Nope. If you place the bar on its end, what is the pressure it creates on the surface that you set it on? So if I'm putting 14.7 pounds onto its end on a square inch, okay, that's going to be 14.7 psi. So if I stand that bar up and I set it down on something like a hand or the floor or my foot, I'm going to be putting 14.7 pounds of pressure onto that square inch of surface, okay? Which 14.7 pounds on a square inch, it's significant. All right, 10. Why does the bar weigh this much? Okay, it is the pressure at sea level. This right here is the atmospheric pressure at sea level. Atmospheric pressure at sea level. So when you're at sea level, you go visit grandma in Florida, but not right now because there's a lot of coronavirus there, okay? When you're there, you're going to be experiencing 14.7 pounds of pressure on every square inch of your skin from the atmosphere, just from the air around you, okay? We don't quite have that much here because we're at 7,200 feet, but 14.7 pounds is the pressure that air puts on every single square inch of your body when you're at sea level, okay? So, 11, how much pressure is on you at all times when we're in Laramie, which is about 76% of the pressure of sea level, okay? So, almost a quarter less than that, all right? And I'll just do that math for you. Here in Laramie, we have 11.2 psi on an average day, okay? 11.2 psi. Remember, in the book, we're talking in different units. We're going to speak in different units. 14.7 psi, that's the pressure at sea level, which is also 1 ATM, 1 atmosphere. That's where that comes from, okay? You're a total atmosphere on top of you at sea level, 1 atmosphere, okay? Up in Laramie, we don't have a whole atmosphere between us and outer space. We only have 3/4 of that. So we have 0.76 ATMs, 0.76 atmospheres on top of us before we hit outer space, okay? That's one way to think about it. Okay. All right, moving on. Part of number 11, do you feel that? Do you feel 11.2 pounds of pressure on your skin? Do you notice that? The answer is no. This is the environment that our bodies were created in. This is the environment that, you know, we have been in our entire lives. We don't feel that pressure because that's what we need. If we didn't have any pressure, our bodies would just fall apart. Our cells would not stay together. If you go into outer space, take off your spacesuit, you're going to explode, okay? So this is the pressure that we feel all the time, and so no, we don't notice it. It's not noticeable, okay? But if I were to hand you that atmosphere bar, and you were to put it on top of your hand, you put your hand on a table and put that atmosphere bar on top of your hand, or if you were to set it on top of your foot and just kind of balance it on top of your foot, it's heavy, okay? If you want to try something similar, you could take a gallon jug, a full one that you haven't opened yet, a gallon jug of milk, gallon jug of water, I don't care. Flip it upside down and put the lid on your hand, like set your hand on a table and put the lid on top of your hand. And that's not 14.7 pounds, okay? A gallon is maybe 8 pounds, okay? Maybe 9. So you put that on top of your hand, you're going to feel quite a bit of pressure on the cap on your hand, okay? But it's not even 14.7 psi. And the area of the cap is probably a little bit bigger than an inch as well. So we're looking at less than half of what the pressure is at sea level. So billions and billions and billions of collisions happening on us all the time. And we don't notice it because, again, that's where we have developed. This is what we need in order to survive. But if you double that pressure, you put that atmosphere bar on you, you're going to definitely notice it. It's pretty significant. Okay, so number 12 says, what does the bar feel like on your hand or your foot? I have no idea because I'm not in class, right? But the second part, what is it meant to illustrate? It's not meant to illustrate sea level pressure. It's meant to illustrate an additional 14.7 psi put onto you. Okay, so doubling the pressure if we were at sea level. So it is definitely significant when you double the pressure on your body. All right, hopefully that was an okay video. Hopefully you enjoyed it as much as possible, and you can watch the next video for the balloon demos. Thanks, guys.